Hello everyone, and welcome to our first lecture in abstract algebra. We'll get right on with it. At the heart of abstract algebra is something called a binary operation. And we define it this way. Given a non-empty set S, a binary operation star, so a binary operation star on the set S is a rule that assigns an element x3 in S to each ordered pair of elements x1, x2 in S. And it's important to note this element x3 in S is assigned to the ordered pair x1 and x2. And this isn't just a pair of elements, it's an ordered pair of elements, so order matters. The assignment of x3 to the ordered pair x1, x2 is denoted in this manner. x1 star x2 equals x3. So here's the ordered pair, x1, x2. The operator acts on this ordered pair, x1, x2, and it assigns to this ordered pair of elements the element x sub 3. Now, the idea of a binary operation is not new to us. We just haven't referred to it in this manner. But let's look at some examples. For the sake of example, let's consider the set of integers z. The operation plus is a binary operation on z. And here's an example. The operation plus assigns the element 3 to the ordered pair 1, 2. So let's see, 3, 1, and 2 are all integers. And so this binary operator, according to this, assigns the element 3 to the ordered pair 1, 2, and it does it in this fashion. 1 plus 2 equals 3. So the binary operation plus assigns to the ordered pair 1, 2 the element 3. Now let's look at a few more examples. No. Let's look at a lot more examples. Another example. We'll take the same binary operation, plus, and the same set, z, the integers. And we'll note that plus assigns the element 9 to the ordered pair 3, 6 in this manner. 3 plus 6 equals 9. So 9 is assigned to the ordered pair 3 and 6 in this manner. And one other example, we're still talking about the operation plus and the set z of integers. The operation plus assigns the element negative 3 to the ordered pair 2 minus 5 in this manner. 2 plus minus 5 is equal to negative 3. So the operation plus assigns the element negative 3 to the ordered pair 2, negative 5. And this example is a good example because we've been doing this since the first grade. But it may be a little bit misleading because we look at this example and it doesn't seem that it matters whether the pair is an ordered pair or just a pair. And in this case, that's true. In this case, the order of the elements in the pair turns out not to matter. But that's not always the case with a binary operation. So let's look at an operation where the order of elements in a pair does matter. Another example. Here we're going to work with the set of positive real numbers, r plus. So these are the positive real numbers. The negative real numbers and 0 are excluded from this set. So given the set of positive real numbers, r plus, the operation divides is a binary operation on the set r plus. For example, divide assigns the element 3 to the ordered pair 6, 2 in this manner. 6 divided by 2 is 3. So our operation, divide, takes the ordered pair 6, 2 and assigns to it another element from the set of positive real numbers. And just to emphasize the fact that a binary operation acts on an ordered pair of elements, let's consider another example. The same operation, divides, it assigns the element 1/3 to the ordered pair 2, 6 in this manner. 2 divided by 6 equals 1/3. So divides takes the ordered pair 2, 6 and assigns to it the element 1/3. Now this pair of examples is good because we're working with the same pair of elements in each case. In each case we have the same pair of elements, but the order is different. Here 6 is the first element and 2 is the second element, and the element 3 gets assigned to 6, 2. Here 2 is the first element and 6 is the second element, and the ordered pair 2, 6 is assigned the element 1/3. So with a binary operation, in general, the order of the elements in the pair does matter. So we emphasize strongly it's an ordered pair, not just a pair, but an ordered pair. Now let's look at some more examples. Here's another example of a binary operation. Let S be the set of all 2 by 2 matrices that have real number entries. And we'll let star, no, you know what? I'm in a star mode right now. Let me change that. We'll let plus be the operation of matrix addition. So the operation assigns to an ordered pair of 2 by 2 matrices that have real number elements a third 2 by 2 matrix that has real elements, and it does it in this manner. This matrix plus this matrix equals this matrix, where each entry in the sum is the sum of the corresponding elements in the first 2 matrices. So let's see, first row, first column is the sum of the elements in first row and first column in these 2 matrices. First row, second column, the sum of the elements in first row, second column of the original matrices, and so forth. And notice that the result is a matrix, a 2 by 2 matrix that has real number entries. So this is a binary operation. And just for the sake of illustration, let's doctor this example up a bit. We'll alter this example just a little bit. We'll look at a closely related pair of examples now. We still have the same set S, the set of 2 by 2 matrices where the elements of the matrix or the entries of the matrix are real numbers. And here we're dealing with the operation minus. And this is going to be the operation of matrix subtraction. From the first matrix, we subtract the second matrix. And it's done in this manner. To this ordered pair of matrices, first matrix, second matrix, we get a third 2 by 2 matrix with real number entries, where the entry in the first row in the first column is the entry in the first row and first column of the first matrix minus the entry in the first row and the first column of the second matrix. And the entry in the first row and the second column of our result is the difference of the entries in the corresponding locations of the first and second matrix. Now here again, order is important. Let's take the same 2 matrices but switch the order. And notice what we get. The entries are different. The entry in first row and first column is A2 minus A1, not A1 minus A2. The entry in first row, second column is B2 minus B1, and not B1 minus B2, and so forth. Minus is a binary operation on the set of 2 by 2 matrices with real elements. And order matters. The order of the matrices in our ordered pair matters. Our binary operation will assign a different result to a pair of matrices depending on the order of the first and the second elements. Two important properties that a binary operation may possess are commutativity and associativity. A binary operation does not necessarily have to have either property, but in our study of abstract algebra, we're going to be very concerned with associativity, for sure. And we are going to be concerned oftentimes with commutativity as well. And here's how we define each. A binary operation, star, on a set S is said to be commutative exactly when x1 star x2 equals x2 star x1. So in other words, we can reverse the order of the elements in an ordered pair, and the operation will assign the same third element to this pair. The ordered pair x1, x2 is assigned exactly the same element as x2 star x1. When that happens, the operation is commutative. And it doesn't always happen. The binary operation star on a set S is said to be associative exactly when x1 star x2 in parentheses star x3 equals x1 star in parentheses x2 star x3 close parentheses. And the idea here is this. We have at least 3 elements, and in the definition exactly 3 elements, but a binary operation only operates on 2 elements. So what do we do with the third element? By the use of parentheses, we can dictate which pair of elements the operation operates on first. x1 star, x2 is in parentheses, so we compute this operation first. And the result is we get a third element from the set S. And this binary operation takes the ordered pair, this element of S, times that element of S, and assigns it a single element in S. Boy, that didn't sound right, did it? I apologize. But the point is, if we have 3 or more elements, we generally have to use parentheses to dictate which pair of elements are operated on first by the binary operation. And if the operation is associative, it doesn't matter which pair of adjacent elements the operation acts on first. Here, the operator star acts on the ordered pair x1, x2, these two adjacent elements. Here, the operation acts on the elements x2, x3 first. If the operation is associative, it won't matter which 2 elements we associate with each other by the operation first. And that's sort of where we get the expression associativity. If the operation is associative, then it doesn't matter which pair of elements we associate with one another first. We'll get the same result either way. If we take the first and second elements and associate them with the operation first, we get the same result as if we take the second and third elements and associate them with the operation first. So if the operation is associative, it doesn't matter which 2 elements we associate with one another first. We can take any pair of adjacent elements and associate them together first, and the order will not matter. Now let's take a look at some examples, some of which may be associative and commutative, some which may be one but not the other, and others which may be neither associative nor commutative. Okay, this is an interesting example. We're looking at the set of integers, z, and the binary operation of subtraction. We've already seen this operation on the integers and noted that it is a binary operation. But we claim that it is neither commutative nor associative. And I guess that should be underlined. Neither commutative nor associative. And just for example, consider 1 minus 3. The ordered pair 1, 3. To the ordered pair 1, 3, the minus assigns the element negative 2. But what if we switch the elements? What if we switch the order of the elements in this pair and put the 3 first and the 1 second? Then the operation minus assigns to the ordered pair 3, 1 the element 2. So depending on which element comes first, 1 or 3, we'll either get negative 2 or positive 2. The same element is not assigned to this ordered pair, or let me say this differently. The element that's assigned to this ordered pair is not the same as the element assigned to this ordered pair, so the operation is not commutative. Not only that, it's not associative either. Consider these 3 elements. 1, 2, 3. And the operation is subtraction. Now, if we don't have any rules telling us how to apply the operation, then we wouldn't know which one to apply first. Now, it turns out in our our system of arithmetic, if an operation is repeated, then essentially we perform the operations in order of appearance from left to right. But let's see if this thing is associative. Can we associate the first two elements and get assigned to this first pair the same element that's assigned to this pair if we associate, I'm not saying this well at all, I apologize. Suppose we associate these two elements first. Will the same value be assigned to this expression that would be assigned to this expression if we associate these two elements first? Okay, let's associate 1 and 2 first. 1 minus 2 is negative 1. Minus 3 is negative 4. Now, what happens if we associate these two elements first? That we have 2 minus 3 is negative 1. So that gives us 1 minus negative 1, which is positive 2. Depending on which pair of elements, which pair of adjacent elements we associate first, we're either going to get negative 4 or positive 2. We don't get the same element assigned to this trio of numbers if we associate these two elements first compared with associating these two elements first. So the choice of which elements we associate first determines the outcome, and the outcome is not the same for both cases. So minus is not associative, and I didn't write that. I guess I should. Hence, minus is not associative Now let's tweak this example just a little bit, and we'll get a binary operation that's both commutative and associative. Here's our next example. The set is the same, z, the set of integers. Here our operation is addition. It's a binary operation on the addition. And oops, I forgot to change that word. It is both commutative and associative. So addition is both commutative and associative on the set of integers. And just for example, we have 1 plus 3 equals 4. What happens if we switch the order of the elements in this pair? And we have 3 plus 1. Well, we still get 4. The order of the elements in the ordered pair doesn't matter. If we switch the order of the elements in the ordered pair, the same element is assigned to the ordered pair either way. Now, what about being associative? Take the same trio of elements, 1 plus 2 plus 3, and we find out that plus is associative. If we associate 1 and 2 first, we get 3, and then we add 3, and that gives us 6. Whereas if we associate 2 and 3 first, we get 5, and that gives us 1 plus 5 is 6. So addition is associative on the real numbers. And actually, these examples illustrate that addition is associative and commutative on the set of integers. It doesn't prove that. I think we just have to accept as axioms that addition is both commutative and associative on the set of integers. Or maybe we can prove it by induction, which I'm not going to do right now. Another example. Let S be the set of 2 by 2 matrices with real number elements. And we'll let star be the usual operation of matrix multiplication. And recall from linear algebra that matrix multiplication is not commutative. And here's an example. The matrix 2, 3, 4, 5, which is A, and the matrix 4, 3, 2, 1, which is B. When we multiply these together, we get A star B, 14, 9, 26, 17. Do that. Check that out and make sure I'm right. But now what happens if we change the order of the elements in our pair? We still have the same two elements, the same two matrices, but we've changed the order. And here's what we get. B star A is the element 20, 27, 8, 11. And please do work that out just to verify that matrix multiplication, even though it is a binary operation, it is not commutative. Is it associative? Well, let's see. The binary operation of matrix multiplication is not commutative, but it is associative. A star B, in parentheses, star C, is equal to A star parentheses B star C close parentheses. It doesn't matter which pair of adjacent matrices we associate first, whether it's AB or whether it's BC. We're going to get the same thing. And just to confirm that, I'm not going to do this out. I have the answer here. But let A be the matrix A1, A2, A3, A4. Let B be the matrix B1, B2, B3, B4. Let C be the matrix C1, C2, C3, C4. And verify that both of these expressions will give us this 2 by 2 matrix down here. It's a homework exercise. So matrix multiplication is a binary operation that's not commutative, but it is associative. And our homework will have more operations to look at. And some will be commutative and associative. Some will be neither. Some will be associative but not commutative. Some will be commutative but not associative. And we want to gain facility with these concepts and a good understanding of them, because the binary operation is at the very heart of abstract algebra. Our next topic is groups, but in order to really understand what a group is, we have to understand binary operations well.